Hello and welcome to Easy Projects. So in this video we will continue to look at LED drivers, and now we will see how to make a switch mode driver. I have been thinking quite a bit of how to make this video because what we're going to do really doesn't make sense, because if you want a switch mode LED driver you just go and buy the chip or a finished module and you use that. It doesn't really make sense to build one yourself, but it's still good to explore the theory and understand how it works. For the linear current sources or sinks, it can make sense to use discrete components and make it yourself, but not really for the switching. It will end up costing you more than the IC, and you will probably not get it as stable as a board IC. Of course there's many ways to make a switching regulator, but I think in this video we will just look at probably the simplest one that still uses PWM. So we will reuse some of the previous circuit from the video about the linear regulator. We still need a transistor to limit the current, else we will just burn out the LED, and we will need a resistor to measure the voltage across, similar to what we did. I chose to do it on the low side. I think that is the easiest when you're dealing with op amps and so on. But there's still no reason you couldn't do it on the high side if you desire. So in between here we will need something in order to make it into a switching converter. So what we need first of all is an inductor. And then we would like a capacitor. And we need a diode here. So this is basically a standard switch mode buck regulator. Normally you would measure the output voltage here and you would regulate according to that. But in this case we want to make it into a constant current generator. So we will, instead of measuring the output voltage, we will measure the output current by measuring the voltage across a sense resistor. So imagine we change this LED, we add more LEDs, less LEDs, put something else instead. The voltage here will change, but we keep the voltage across the resistor the same. So no matter what you put in here, you'll pull the same amount of current. The question then becomes, how do we drive the transistor? So if we want to drive the transistor with a continuous PWM signal, I think the easiest way to do that is to generate a sawtooth wave and then compare it to a function of the output voltage. So something like this. So if our aim is to have 1 volt across this resistor here, we can make a circuit that will integrate the error over time. So say if we have 1.1 volt, that means we want to lower the voltage, and the output on this side should slowly go down. We can do that with an integrator. So as long as the voltage here is lower, the output will continue to decrease over time. Once it is at the correct voltage, it will stay stable, and once it starts to decrease, the output will go up. I think this would be the ideal solution, but if we cannot get it stable, maybe we can do something else, but I think I will give it a try. We feed that into a comparator and we compare it to a sawtooth wave. And that is what generates the PWM signal for the transistor. Over a short period of time, the output here will look like a horizontal line. And if we compare a horizontal line to a sawtooth wave, you can see we will get a PWM signal. Say we have the line here. That means we will get Basically we get a high every time the sawtooth is greater than our reference here. The diode here shouldn't really be necessary if we use a proper integrator here, because the response should be slow enough that it will be cut off by the sawtooth. If we want to make a poor man's triangular wave generator, we can make it like this. It is basically a comparator with a hysteresis, and the output feeds back to the input, but it has an RC filter. So when we start up, we set a reference, in this case 2.5 volts we want to set at the non-inverting input, but the op-amp here will be in a state either high, fully low. It wants to go either way. It can do that because we have a resistor here, so the output can jump to the high rail or the low rail. It will then affect the input voltage on the non-inverting input, setting it to some voltage, which would be the divider here with 10K parallel to 4.7K to either of the rail, depending on where it decides to go. Let's say it goes high, then the output will charge this capacitor, and when we hit this set point here on the output here, it feeds back to the inverting, and the polarity will flip on the output, so it goes low. It takes some time to discharge the capacitor to the new reference, and once we hit the low point, it flips the output again and wants to charge up, charge down, up, down, so we make a triangular wave. But it is not truly triangular because we are feeding the capacitor with a fixed voltage. If we wanted a true triangle, we would feed it with a constant current. So what we end up with is something that looks more like this. So it is rounded a bit. This would be good enough for our crude experiment here, so that's what we will use. But we would like to cut the back end off here and just make it a sawtooth instead of a triangle. We can do that by allowing the op-amp to eat away all the current at once when we go negative, but slowly charge up. We can do that by adding a diode in this direction across the resistor here. If we want to be kind to the op-amp, we would add a little bit of resistance anyway, say just like 1 ohm something, so we don't directly short the output into a capacitor. The capacitor is, in theory, it can deliver infinite current over a very short period of time. It has ESR and things like that, and most op-amps are protected so that you cannot destroy the output anyway, but it's good practice to put it there. You might think this diode will do something to the output, so it's not a completely straight line because it has a voltage drop. But this generator here doesn't go all the way to either rail, and that means we have some wiggle room to allow for the drop of the diode. So actually we will not see it in the output unless you put this division ratio so that the output goes very close to the rails. So I've built up a circuit here. I used 150 nanofarad instead of 100 because that's what I had laying around. And I added some a decoupling capacitor and just some bulk capacitance on the supply rail. So let's turn it on and see if it works like we expect. So I am probing the output of our sawtooth generator, and I'm ready to turn on the power supply. And as you can see, it looks kind of like a sawtooth, but you can see the charging of the capacitor. We have a rounded slope. It could be fixed by adding a few more components, but I think in our case it's not really necessary. We will be regulating anyway, so it can take into account that it's rounded. If we zoom in, you can also see that the negative going slope is not very fast. It's just because of the op-amp that I'm using. But it should be fine also. I can try to remove the diode so we can make a triangular generator. We can also invert it quite easily so that we have a fast rising and a slow falling edge just by flipping the diode. And the frequency, you can calculate it if you want. I didn't really bother, I just tried something, but it's the RC time constant of this resistor and this capacitor over the voltage range that you set with the division ratio here. If you increase this resistor, you will squish the peaks together and making a faster wave also. If you change either the resistor or the capacitor, you will have the same amplitude but only changing the frequency. So we looked at the sawtooth generator, so now let's look at the integrator. That's even more simple. We only require 3 components: an op-amp, a capacitor and a resistor. So the way this works is we set a reference on the non-inverting input. It could be 0.5 volts. And then we set the input here to 0.5 volts also. That means there's no difference between the two inputs, and that means the output will do nothing. Let's just say the output is at 0 volts. Actually, this is inverting, I noticed, but let's say the input here goes a little bit lower than 0.5 volts. If we didn't have this capacitor, it would just be a comparator and the output would go high immediately. But when we add this capacitor, the energy goes through the capacitor and charges up this point here. So when it just drops a little bit, that means the energy from the capacitor is able to keep the two inputs at the same potential, and the output doesn't rise up to 5 volts. But this energy slowly flows out through the resistor here and also into the input. So it leaks out and more energy has to be applied through the capacitor. But the only way we can add more energy is to rise the voltage. That's the only way we can push current through a capacitor. So that means as the current is leaving this resistor, because that's a voltage drop, we need to add more voltage on this side to keep the two inputs equal. And that will look like a linear ramp. So we go from 0 volts and we go slowly up to, say, 5 volts. Once we hit 5 volts, the op-amp can no longer operate as an integrator. It only works within the supply rails, of course. The slope here, you could imagine we could go much faster, or we could also go like slower. The slope here depends on the differential between the two inputs, and also the slope down would occur if this voltage is higher than the reference. A little bit higher we will have a slow ramp, much higher we will have a very quick ramp. And you set this resistor capacitor time constant to give you the slope that you want at a given difference in the voltage. So I built the integrator here, and it's above this line. This down here is the old circuit. It looks more complicated because I had to set the resistive dividers to provide the references. One I'm making with a potentiometer. I added a very high resistor across the capacitor just to take off some noise. So it is a little bit difficult to show that it's linear, because when I turn the potentiometer, of course, I'm turning it while the output is changing, and that makes it into a curve. Okay, so that's more like it. It looks like my resistor across the capacitor was actually doing more harm than good. I thought I picked a high enough value that it wouldn't really matter, but the problem is, as you saw, it allows the output to be a linear function of the input, which we don't really want. Okay, yeah. Yeah, now it works better. So the idea is that in our final circuit you would not see a ramp as the output of the integrator. You should see a straight line somewhere in between the two rails. The reason we don't see a slope is because the regulation will make sure that the voltage drop that we measure is always a little bit higher, a little bit lower. So as soon as it gets higher than our reference, this will start to decrease, and when it gets lower it will start to increase. So what we would see is just a little bit of ripple going on a horizontal line. That's the idea anyway. It could be a little bit tricky to get it stable with discrete components. So I hooked up the two circuits together in a comparator, and you can see we get a 100 Hertz square wave. I didn't hook up the input to the integrator, so it's basically just taking the 50 Hertz hum from the mains. If I touch this with my finger, you can see that it switches around, and we do get some kind of PWM signal going on. I will hook it up to a fixed voltage, and I can try to adjust the reference. So now I hooked up a reference, and I can adjust the input voltage with a potentiometer. I coupled it together with the sawtooth generator into a comparator, so the output should be a square wave where the two overlap. So what we expect to see now, as the slope rises, we expect to see an ever increasing duty cycle that goes, now it's, you can see it's low, so we expect the end result to be 100%, and in between we want to see an increasing duty cycle at the frequency set by the sawtooth generator. It's probably difficult to see when it's rolling like this, but let's make a single capture. So we start by basically nothing, it doesn't even go fully on, and then it increases and increases and increases until we basically see the opposite. So now we have a PWM generator that can regulate according to the set point. So what we just did was to take these two and put into a comparator, and we're looking at the output. This input here should go to the sense resistor, but right now I had a potentiometer here and the reference was just set at 0.5 volts. What we want to do now is build the rest of the circuit. So select an inductor and a capacitor and the sense resistor, and then set the reference current. The reference current can be a potentiometer, so it's adjustable. The only thing to consider is that the current should be within the range of the conduction of the inductor. So you select your inductor according to the switching frequency and the current. So finally I put everything together in this circuit here. We have the sawtooth generator, the integrator, and the switching regulator. And then we take the feedback from across this resistor, so we get the current as the regulating parameter. Right now I don't have any LED, I just have basically a heater. It'll just burn power, but it should work with any load in here as long as we don't require more than 5 volts. I rearranged this to use a PNP transistor so that in theory we could use a greater voltage. So let's see what happens when we turn it on. And I'm measuring the output here, and we get a not so clean wave, but probably because it's made in a breadboard. We have the kind of normal looking switch mode regulator waveform here. It's just we have too much resistance, so it's a bit high ripples. Let's see if we can adjust the output current. I should be able to do that by adjusting this potentiometer. We expect to see the output voltage go up as well as we increase it, because we are basically just measuring across a resistor, so voltage and current should be in a linear relationship. I think what's more interesting is if we measure the PWM output. It should be this guy right here. It's not a very sharp waveform, as you can see, because it's not very good op amps also. If we increase it, you can see the PWM goes up and up and up, and as we decrease it, it goes down, and once we hit 0, it basically is off. The current draw you see on the, or you should have seen on the power supply here, is including the quiescent current for the entire breadboard. So actually I must say that this circuit works a lot better than I have thought. The PWM is just dead stable. I've tried to make something like this before, but with higher frequencies, and it just really ran away and was only marginally stable. Oops, I hit the current limit on the power supply. So I have added the LED here, and I also added a separate power supply for the VCC. So now only the control circuit is powered from 5 volts. That way I can also see how much current we actually use from VCC. This meter here is measuring the LED current. I'm measuring the voltage drop across the resistor. Currently 18.5 milliamps. And over here we have the input voltage and current. So we're feeding our power supply with 8.4 volts, and you can see the current is 8.25 milliamps. If we compare that to 18 milliamps for the LED, you can see that we're definitely better than the linear regulator. It is still not a very good efficiency though. Remember, the voltage drop across the LED is around 1.8 volts and 200 millivolts across the resistor. So that gives us roughly 2 volts. If we say our current is half but our voltage is 4 times, that would give us an efficiency of about 50%. which is not great, but it's better than a linear. Again, this circuit was really only just to play around. It wouldn't make sense to make your own. Just one of the things that contribute to the fairly low efficiency is, first of all, the DC resistance in the breadboard, and also losses in the transistor and the diode. If we see the scope here, the yellow line is VCC and the blue line is on the collector side of the pass transistor. So that would be right here. When the transistor is on, we expect this voltage to be approximately the same as VCC. It has a little bit of saturation voltage, it should have that, but in a good circuit we would have as little as possible. But you can see in this case here, when the transistor switch is on, it goes to VCC. I can scale it up. It does go to VCC in the beginning, when it starts to push current through the inductor. It's like an open circuit when it just starts. But when the inductor starts to conduct, we have a drop across the transistor. And that's what you can see, the blue waveform dropping here. And the part that's missing from the square here, that is losses. But you can also see that the VCC drops as we start to pull current, and that is because of resistance in the wires and in the breadboard, and that also gives us some losses. When the transistor switches off, you can see the voltage drops all the way below zero here, and that's because the inductor wants to keep pushing current. Now we got it started, it doesn't want to stop again, but the diode catches that, and it's able to complete the loop through the ground so that the inductor can get rid of its energy. As long as the line is low here, that's when the diode is conducting, and once it stops we have some ringing, probably due to some stray capacitance, and perhaps my long ground leads on the probe doesn't help either. But actually the regulation is quite stable. You can see when I turn the voltage knob here, the current through the LED doesn't change at all. When we go low enough, it will of course start to drop out, and then we lose it, but it only changes a few microamps really when we adjust the voltage. It also shouldn't matter what the load is. Right now we have a drop of 1.8 volts, but if we have a larger drop of maybe more than 3 volts with this 1 watt LED, oops, you can see we get exactly the same current, and we can still adjust the current with the potentiometer. We can go way down. We can also go higher. Around 100 milliamp we really start to punish this poor transistor here. Because it's a switch mode supply, it needs to conduct more when we're charging up the inductor, and this poor little transistor simply cannot do that. It's not spec'd for it, so if we wanted to do that we needed a bigger transistor. So I think that's it for our homemade regulator here. Perhaps we should look at a bought one that has a much greater efficiency. So the chip that I chose is the NCV3065. The reason why my choice fell on this chip was mainly the price. It's around $1.5 a piece for one-off quantity. It goes up to 1.5 amps, and it's a constant current switching regulator for LEDs. That's really all I had time to read before I bought it. It turns out it's not as good as I hoped, but what can you expect when you don't really read the datasheet? It takes a wide input voltage range from 3 volts to 30 volts, and the feedback voltage, they say it's low at 235 millivolts. I wouldn't necessarily call it low, but it's not high either, and it has a cycle by cycle current limit. It needs no compensation, and it can operate up to 250 kilohertz. Because it's a constant current supply, we can actually operate it without any output capacitance, because the LEDs don't really mind if they get a change in the current over time, just as long as the average current is what they expect for. And of course not exceeding the maximum short-term current. There's a typical application diagram here, and that's basically just what I built up. I changed the resistor values a bit to give me the current that I need. And then I went to my garage and etched a quick board. It's not really that good. It's basically just a single layer board with a ground plane on the back also, and then 2 capacitors. There's no traces on the back, so I just drilled through and removed the copper around the holes. Some of my ground plane got trapped on this side, so I had to drill through and make some VS. I chose the SOIC package because it's fairly easy to solder on a board by yourself, and it's also not as big as a dip package. You can actually get this chip in a dip package if you want, but for what I want to use it for, maybe I would like to keep it small. I thought about making some LED lamps by myself, and for that I don't really think I will be using this circuit board. That was just a quick test I made in a few hours just to test the chip. Apart from the regulator, I just used parts that I had laying around. Perhaps the inductor is also larger than it should be. And I could use smaller resistors, but here I just have 0805 resistor kits, so that's what I used. And some old, probably not very good electrolytic capacitors. And then in parallel with some ceramics, just to knock down the impedance a little bit. You can see the circuit is really simple. I don't think we should go into details with all the components, because if you buy a different chip it will vary, but it has some components to set the frequency, and it has the pulse by pulse current limit set by this resistor here. The average current is this resistor down here. This node here is where it expects to see the 235 millivolts. So you calculate your current by 235 millivolts across whatever resistor you put here. Apart from that, it's a standard buck regulator. You have your transistor inside the chip, and it turns on or off the SWE. When it's on, it pushes current through the inductor and pushes current through the LEDs. If you don't have the capacitor, then it just pushes current through the LEDs. When it turns off, the inductor still wants to push current forwards, and since this is off, the voltage here tries to go negative, because if a current is flowing, there has to be a potential difference. To complete the loop here, we put a reverse biased diode here, and the current can flow through the loop here. It works like a standard buck regulator, except that we measure the output voltage across a resistor to ground, just like we did in the regulator that we made ourselves. It's possible to add your own transistor on the output to drive more current, but I didn't really look into that. We have some graphs here showing the efficiency, and this one is for no output capacitor, and these two are with output capacitors. One at 350 milliamps and one at 700 milliamps. The lower graph is for a single LED, which has a drop of 3.6 volts. The top one, 7.2 volts for 2 LEDs. They wrote that somewhere in the text. As you can see, it's a little more efficient at higher currents when the voltage goes up. Over here it's at 60 and 68%. Here it's 68 and 76 at like 34 volts. I'm using a much lower current, around 23 milliamps I think, so my efficiency might be very bad. I don't really know that yet. For the lamps that I'm making, I'll probably run it at around 200 milliamps, so also even less than this. When I said the chip doesn't seem to be as good as I hope, I'm referring to these graphs here. It's pretty good here at around 80–85%, but as the input voltage goes up, you really lose the efficiency. My idea was to run it at 12 volts for 2 LEDs in series, so it might not be that bad. But should I decide to use 24 volts instead of 12 volts, I might not want to use this chip because the efficiency would already be down to less than 70 maybe %. It might still be okay, but if I could find a better solution for a similar price, I obviously would go for that one. The chip can also be used as a boost converter. I didn't look into this at all, and they say that you can actually adjust the current by putting either a PWM circuit on the comp pin or also using an analog voltage. I did add the option to put a potentiometer on my PCB here, but I haven't tried it yet. I hooked up the power supply to the PCB through an ammeter so that we can monitor the current going into the board. And I know it's not going to blow up because I already tested it. So the board is using about 21.5 milliamps. But that really says nothing about the LED current now that it's a switch mode supply. So we need to put an ammeter in series with the LED and also measure the voltage drop across the LED. So trying to keep everything in the frame, we have the LED voltage, LED current, and still the supply voltage and the supply current. So we can see the board draws 21.5 milliamps, the LED current is 26 milliamps at 3 volts, and the supply is 7 volts. To calculate the efficiency, we take the output power and divide it by the input power, and we get the power by multiplying the voltage and the current. In this case I get it to around 51%. If I increase the voltage, we see the input current goes down. Let's choose 12 volts. We see the output current does increase a bit. We didn't really expect that, but I guess it's okay for a small amount. And now we only get an efficiency of 45%. We are running a pretty low current though, well below the examples from the datasheet. And the LED, it's not even warm, so I guess we can increase the current. Let's say double it to around 50 milliamps. Changing the current was as easy as just changing the resistor, but in this case I just piggybacked another 10 ohm on top of the 10 ohm that I had already. Now we expect approximately 50 milliamps. And we get 53, and we can now calculate the efficiency again. It is now 54% at 12 volts. Let's try again at 7 and see if we can get that. And that works out to be 58.6%. Still not very good, but again it's a pretty low current compared to the datasheet. If you want to drive lower current LEDs, perhaps this is not the right chip. But I think for higher currents it would be okay. I can try to hack in a 1 ohm resistor and momentarily run it at 230 milliamps. I didn't have any surface mount 1 ohm resistors, so I just used a leaded. Actually I chose 1.2 ohms because I already have 5 ohms SMD on there. So I just put it across it so I can pull it off again. We have to be fairly quick because the LED will warm up very fast at 200 milliamps. So we get 160 milliamp draw and 200 to the LED. It's actually not even that warm. It's still not super good efficiency. I get around 68%. It might be the diode that I'm using that's not really up for the job, and also perhaps there's too much losses in some of the other components. And maybe the switching frequency is not really right for the inductor. Also there might be some drops in the leads here that I didn't take into account. It shouldn't be that much at 200 milliamps. And this reading could be off by 50 millivolts. It's not high precision testing, it's just kind of getting the idea. Anyway, I hope you liked the video, and if you did, please give it the thumbs up. And let me know if you think we should make some lamps with a circuit similar to this. Anyway, thanks for watching the video and see you soon for the next one. See ya!